All right, day 8, Advent of Code. We've already finished the first 7 days. If this is your first time tuning in, please like and subscribe. We're going to get into it. We're going to try to get all 12 days this year. So let's get into day 8 right away. Playground. Equipped with a new understanding of teleporter maintenance, you confidently step onto the repaired teleporter pad. You rematerialize on an unfamiliar teleporter pad and find yourself in a vast underground space which contains a giant playground. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they have suspended a large number of small electrical junction boxes. Yo, Alpha, what up? Yo, I might need your help for this. You should try this out. Day 8 might actually be difficult. But I appreciate you. Their plan is to connect the junction boxes with long strings of light. Are you doing work? Damn, they got you grinding, man. Yo, you're gonna move up fast. But their plan is to connect the junction boxes with long strings of light. Most of the junction boxes don't provide electricity. However, when two boxes are connected by a string of light, electricity can pass between the two junction boxes. Okay, it makes sense. The elves are trying to figure out which junction boxes to connect so that electricity can reach every junction box. They even have a list of all junction box positions in a 3D space. Ooh, in a 3D space? Nah. The list describes the position of 20 junction boxes, one per line. Each position has an X. This is like some linear algebra stuff. Each position is given an XYZ coordinates. So the first junction box is at list X162. To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are close together as possible according to straight line distance. Okay. Might be some Dijkstra's. Because it's already talking about some shortest distance. In this example, the two junction boxes which are close together are 162, 817, 812, 425, 690, and 689. By connecting these two junction boxes together, because electricity can flow between them, they can become part of the same circuit. After connecting them, there is a single circuit which contains two junction boxes, and then the remaining 18 junction boxes remain in their own individual circuits. Now the two junction boxes which are close together but aren't already directly connected are 162. Okay, after connecting them are 162, one like this random one, and 431. Okay. Since these are already connected to another junction box, there's now a single circuit which contains three junction boxes and an additional 17 circuits which contain one. Dude, there's like some minimum spanning tree. Some minimum spanning tree MST question. Either like a Dijkstra's or a minimum spanning tree where we just try to connect all the ones that are closest to each other and just keep doing that until all of them are connected. The next two junction boxes to connect are these two. After connecting them, there is a circuit. Okay. The next two junction boxes are 431 and 425. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They would like to know how big the circuits will be. After making the 10 shortest connections, there are 11 After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 junction boxes, one circuit which contains 4 junction boxes, and two circuits containing 2 junction boxes each, and 7 circuits which each contain a single box. Multiplying together the size of the 3 largest circuits produces 40. Your list contains many junction boxes. Connect together the 1,000 pairs of junction boxes which are closest together. Afterward, what do you get if you multiply together the sizes of the 3 largest circuits? This is like a minimum or like a heap question. This is like a heap question. See the puzzle input. Okay. Let's see. Might have to bring out Excalijaw. Well, like we just have like a bunch. The way I'm thinking about this first question is, suppose we just have a bunch of points on the map. The algorithm says like to focus on connecting pairs of junction boxes that are as close together as possible according to straight line distance. So maybe it's just a heap. So we just need to figure out for each point what's the distance between this point and all the other points. So we need to, and then we need to pick the smallest one. Okay, maybe what we do is, I think to get the straight line distance between 2 points, we could just use the Euclidean distance. Yeah, we can use the Euclidean distance formula to get the distance between 2 different points. And then we could just do that for every single point. So with every single point, we see the distance between these points, these points, these points, these points. And then we do that for every single point and then just throw them in the heap. And then we just pop up the 2 smallest ones and then connect them. And then once we connected them, we can put them in some sort of scene set to just know that we've seen like that those two are already in a circuit. But how do we know they're in the same circuit? Okay, that's the hard part. It's like a union find. Wait. That's the hard part right here. Yeah, it's sort of like a union find because we need to know if they're in the same circuit because once we connect them, that becomes one circuit for the same circuit. After connecting them, there's a single circuit which contains 2 junction boxes and the remaining 18 junction box. Now the 2 junctions which are close together but aren't already connected are 162 and 81 and 431. After connecting them, there is now a single circuit which contains 3 junction boxes and an additional 17 circuits which contain 1 junction box. Four, three, one, and 14. Because wait, how does that work? Okay, let me think this through. The next two. Now I'm just trying to think of this case. So let's just say. So we have one. Oh, so we have 162. We say 162 connects with 425. There's like a minimum spanning tree. Yo, what's up? Squid, this is a hard one. In this example, so they're close together, so we just connect them, right? By connecting these two junction boxes together, because electricity can flow between them, they become of the same circuit. After connecting them, there's a single circuit which contains two junction boxes, and the remaining 18 junction boxes remain their own individual circuits. That makes sense. Now we connect two boxes which are close together but aren't already directly connected. So we have 162, 817, 812. It says the other closest one is 431. So let's do this. So they're not in the same circuit yet. So we go like that. After connecting them, since 162.817 is already connected to another box, it becomes the three junction boxes. That makes sense right there. The next two junction boxes are two like random ones. Okay, that makes sense, right? So like two other random ones connect to each other because they're the shortest. Dude, this is like a union find type question, honestly. Because now these connect, but we're just like unioning based on the minimal. After connecting them, there is a circuit containing three. Okay. The next two junction boxes are 4 3 are this one and 425. So we just need to so we have 431 and 425, right? But since because these two boxes were already in the same circuit, then so we don't connect them. So like, do we not connect them there, or do we still connect them? Does it even matter? 5 junction boxes, one circuit. Which why wouldn't they just do this in a 2D space? Why do they have to make it 3D? So now, like, this is where I want to get a clarifying question. This process continues for a while, or like, do we make this connection or not? I mean, I could probably try to code it if we make that connection. Dude, okay. Like, I can try coding it, skipping that, and one like not skipping that, and at the end, we probably do want to skip it. Two circuits which contain two junction boxes, and 7 circuits which contain a single box. Okay. I mean, I guess we just have to get into we just gotta straight code it. But the thing that I'm just wondering right now is if they're already in the same circuit, do we connect them? Because if we don't want to connect them if they're already in the same circuit, then we have to do like some sort of union find. That's pretty much it. But I think what we need to do first, what we need to do, yo Caesar, what's up? What we need to do first is just generate the distance between every 2 point and then like throw them in the heap. And then like once we have a heap, we just start connecting like the ones that are close together. But we have to use the Euclidean distance between the 2 points to find like the distance between the 2 points in the 3D space. Straight line distance. Is it gonna give us this? Oh yeah, it literally gives us. Yeah, it just says what happens if it's a 3D space. Yeah, it's just this operation right there. Okay, let's get this started. And then maybe we just like have to loop 10 times, and then like perform a DFS or something. Like once we make all the connections, we just make like the first we just make a connection based on what's shortest, and then we'll just DFS on every single node and just figure out the number of connected components essentially and return that. So that's part one. Let's see. Ramen, what up? Ramen, have you tried this question yet? Come on, what's up? Yeah, it's perfectly fine, man. Good thing it's only 12 days this year, so if if you fall behind, you can easily catch up. So we're getting to day 8. CD day 8, 3, part 1. We're line in. So we're gonna have to split it. And we'll say for we're gonna have our points. We're gonna have our points here for line in input string. What we're gonna do is we're gonna get our x, y, and z coordinates by doing line dot split on the comma, and we're gonna do points dot append like a tuple of the x, y, and z, but we'll cast them to integers. X, y. Now we have the points. Now we need to compute the distance between every single point. And then we're gonna push that into a heap. For x for p p1 x p1 y p1 z in range length of points. We're gonna extract the point here for I. We're gonna do a double for loop to compare the distances between every single one. I plus 1. We'll do equals points I. Go to this. P2, P2. Now we just need to compute the distance. P1. We need to compute the distance between the 2 points. Yeah, I guess we don't really need to extract this. We can just go like this. P1, P2, and then we have to return like the square root. Math dot square root of like all these points, the distance between all these points added up. So distance between P1, this. Pretty sure that's a Euclidean distance formula. But they give it to us right there, so we can just verify. Oh, we got a square root, or yeah, or not square root. We got to take it to the power of 2. P1 minus Q2. P1. Take the square of both of these, and then what we'll do is this equals distance. How's day 8? It's it's pretty interesting. So we're given a bunch of points in a 3D space, and then we just need to start connecting. We're essentially given points in a 3D space, and we need to connect the points that are closest to each other, like 10 or 1,000 times. Like we have to do it for the first 1,000. And then like one thing I'm not sure about, it does mention this a little bit, is if they're already in the same circuit, if and they're like the next closest, do we want to connect them? Because if we don't want to connect them, then we need to do some sort of union find to know that they're part of the same circuit, and then like move on to the next one. So I'm just implementing right now. Yeah, I think it might be like a union find, but I don't know yet for sure, because we might just connect all the small ones. But once we connect like the first 1,000, I think all we need to do is like a DFS to find a DFS on every single node to find all of the connected components, and it's essentially like just finding the number of connected components. It's a lot of more code than some of the other ones. Advent of Code is just a challenge where they just like every day before Christmas they drop a new coding challenge, and it's like sponsored by Jane Street and a bunch of hedge funds. Yeah, you determine, Paul, essentially what you do is you look for you just follow this algorithm. You start off by looking for the first two boxes that are closest together by straight line distance, and then you connect them, and then they form a circuit. And then after, you take the next two ones that are close together, and then you connect them, and you form a circuit, right? The part where I'm confused is it says the next two boxes are like they're already part of the same circuit, and it says because these two junction boxes are already in the same circuit, nothing happens. But does that mean like we skip over it, or do we still connect it and like it just doesn't form a new circuit? Dude, that's crazy in Rust. Okay, maybe like I think maybe the follow up they're gonna be like don't connect it if they're already in the same circuit, and then we have to modify our algorithm for like a union find. But yeah, that's what I'm implementing so far right now. So we get the distance there, and then we're gonna push the distance between the 2 points into our heap. Um, this points. Damn, I haven't used the heap in a while. But I think you just do this points. And then the first parameter is actually the distance. And then we could just put the 2 points. What? Wait. What's going on here? Okay. I think it works because the closest one are 162 on the heap, 162.817.812, and 425.689. Okay. I think that's yeah. I think our heap is working correctly. So now we just need to do something. I don't know if I have to do union find yet, but we'll see. Because what I can do is just like run it for X amount of times. So it told me to we just need to run it after making. So I'm gonna loop for 10 times and then see if I get the same result. So what I'm gonna do is I neighbors. So I'll add it into a neighbors array when I connect them. Point A and point B equals heap Q dot heap pop, and I'll just pass the this points. Right. Then I'll put nabs dot append point A, point B, something like that. Yo, what's up, man? When's the next time I'm hosting a Q&A? We can do some after. What's your questions? But how do I know how we need to like we're gonna do a DFS at the end. This. So now we have our neighbors. We know all the neighbors. Now what we're gonna do is we're gonna start a queue. We'll just do a DFS. We'll just do a DFS for every single point. And we're gonna count like the size of each. The size of each. Size. So we're gonna have like we have all the neighbors. Now we kind of just need to like perform a DFS on each one and then figure out the size. And then we're also gonna have like a scene set. And then what we're gonna do is for point in points, we're gonna do some work. Just okay. We're gonna perform our DFS. So let's just implement that quick. We're gonna be given the the point. We're gonna be given the scene, And then we're gonna be given the neighbors, right? Stack equals point. And we'll scene dot add point. While stack okay. Yeah, we can get through that. You have good experience because you're working at you've worked at Synopsys, which is pretty well regarded. Where do you live? And chat always has good advice. Chat will always give you good advice too. Every time people ask me questions, like if I'm working on a question in the middle of an interview, like they always give good advice too. But it's pretty good. It's performance review season, so we'll see how it turns out for me. So what we're gonna do is we're gonna perform a DFS. Stack dot pop. Oh, we're gonna need to build an adjacency list. So default list. If names of point A dot append point B and reverse. So we're building out an adjacency list. For neighbor in names of the point if neighbor is in scene, continue. Otherwise, stack dot append size is 1. Stack dot append the neighbor, and we'll do scene dot add the neighbor node size plus equals 1. Return the size. Sizes for if point inside in scene, continue. Then we'll do a sizes dot append DFS on the point in the scene and the names. From collections, import default dot sort reverse. I can't believe I still remember this Python syntax. I barely use Python. No, we just add up. Okay, so we just add up like um we're just gonna add up the last 3. Equals sizes. The first 3. Print x plus y plus z. Or multiplied. We have to multiply. 40. All right, get this. Let's go with the large input. That's a lot of coding. So we need to run this 1,000 times. Let's go. First try on the first part. Last year I wouldn't have been able to solve that right on the spot like that. All right, let's get into part 2. The L's were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they're all in one large circuit. Continuing the above example, the first connection which causes all the junction boxes to form a single circuit is between the junction boxes at these ones. The L's continuing the above, the first connection which causes all of the junction boxes to form a single circuit is between the junction boxes at 216, 146. The L's need to know how far these junction boxes are from a wall so that they can pick the right extension cable. Multiplying the x coordinates of those two junction boxes produces this number. Continue connecting the closest unconnected pairs of junction boxes together until they're all in the same circuit. Okay, this might be a union find. Paul, what do you mean? We had to do like 5 different patterns just to get that working. You're too cracked if you think that's easy. That's at least a medium. Continue connecting the closest unconnected pairs of junction boxes together until they're all in the same circuit. What do you get if multiple of the last two junctions you need to connect? Okay, wait, let's read this again. And this is just day 8. We're gonna still do day 9. People, Paul, people were telling me that they spend 3 to 4 hours even on day 2, day 3, day 4. Like that's what they're commenting it. Oh, really? There's an echo? No way. Y'all hearing an echo? Test, test. Okay, okay, okay. I know Paul has like really good. Wait, let me see. I'll test it myself. Wait, there's no echo. Definitely no echo. Okay, the L's were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they're all in one large circuit. Continuing the above example, the first connection which causes all of the junction boxes to form a single circuit is between the junction boxes at these two coordinates. The L's need to know how far those junction boxes are from the wall so they can pick the right extension cable. Multiplying the x coordinates of those two junction boxes produces, okay. Continue connecting the closest unconnected pairs of junction boxes together until they're all in the same circuit. What do you get if multiplying the x coordinates of the last junction box you need to connect? Bro, this is just like a union find. Okay. Let me see if I can pull a union find out of nowhere. I literally haven't implemented that in a while. Class. Union find. Union. Self. Find. X and Y. No problem. Self. Wait. Let me think if I could just brute force this. Self dot sizes. Self dot. Oh, you can probably union finder. Or do like, wait. Because when I connect 2 points, right? Oh, man. When I connect 2 points, I need to like check number of components. So when you connect two points, we just need to check the number of components, and it needs to decrease. So maybe we can start at like 1,000, right? And then we just need to check when we do the union, if it returns a false, if it returns a true, that means we made a join. If it returns a false, that means that we did like they're already connected. So if it returns true, we decrement, and the moment we get to the first 1,000, we know point A and point B. We just multiply that and print out that result. So we don't need to do this extra part right here. All right. So I'm just gonna actually duplicate this. So we can kind of remove this DFS probably. So we're gonna do a union and a find. Self dot parent. Okay, how are we gonna do this? Okay. I work on products team. I work on products team. I worked products pretty much all my life. Find x parent y equals self find y. Damn, how did I do a union find? First, I need to find the parent. right? And then if the and then like I need to update the sizes depending like on the size of the parent. So what I'm gonna do is when I do a find, if x if x in parent, that means we're gonna capture parents. If x in parents, else we return out like something like this. If x self dot yeah, hello interview is really good for that. Self dot find parent y. If parent if so I'm gonna find the parent. If x is has a parent, then we have to like find the parent and we're gonna return that. Otherwise that. Then we're just gonna say at the end we're gonna say the parent of x is equal to the parent of x is equal to parent x. And the parent of y is equal to parent y. So this just kind of tells us return if these are equal. If parent x equals parent y, return false. Then of x. Union find, it's finding like it's like these are the 2 points. It's connecting the 2 points, right? Like when I say x and y, I just mean p1 and p2. So size of x here. Yeah, I'm gonna connect that here. Sizes of yeah. But you have to connect them based on the size. If the size of x equal to size of y, z. What's the size of Bro, I haven't done union find in like years. Not years, but like at least 6 months. Size of x equals y, then go. Then it doesn't even matter. We'll just make the connection here. We'll say the parent of x equals the same parent as is equal to parent y. Then we'll say sizes Did I delete? Okay, sizes of parent was sizes of parent x plus equals 1. This is probably like not even correct, or if size of x is greater than size of y, dude, we could just do something greater. I'm gonna do this. I don't know if I'm even doing the compression right, but we just do that like that. I'll look over this in a sec. So I'll bring the union find and just correct me if I'm wrong, chat. I think that's the gist of it, but um it's not even syntax right here. How is it? What day am I on? Oh, I'm only on day 8? Oh, shoot. Yeah. I don't even know. I haven't implemented this in so long, but we'll see. UQ. Well, distance points. If, or what we're gonna do is like we're gonna do a union. U circuit equals DSU dot union point A point B. If new circuit, then we kind of have to make like 1,000 connections or 999 connections. Or like largest size. The largest size has to kind of bro, okay, if the new circuit, if we do a DSU, if it's a new circuit, that means we connected. So how many connections do we need to make in order for everything to go? I feel like it's like 999 or something. Or 1,000. Right? So if we have 10, or let's just go with a small example, we have 3. We go 1, 2, 3. Or just N, isn't it? So if we had 4, these already 4. 1, 2, 3, 4. I think we just need N connections. So if we have 1,000 nodes, Yeah, you're right. You're right. You're right. You're right. You're right. Yeah. So let's start with the. Dude, this is a hard question. Only because I haven't done Union Find in a while. What? Why did I implement that twice? Self parent x dot find missing one positional argument. Oh no, with find. Oh, we just put like. Oh yeah, we just put like one here. We this like that like that. Where's that? Yeah, yeah, yeah. Parent. What? Where is this? For a parent. If x in self dot find parent x. Oh my god. Woo! Recursion to the max. If x in self dot parent. If it has a parent. I think we lit. It's like this. This is this compression there. Size can go up by greater than one. What do you mean size can go up by greater than one? If x is in parent, we look to we return that. Otherwise, we return x. So like if it's not in there before, it just has its own parent. Wait, where? How is it like? How is it recursively going all the way to the top? Like where's my why am I getting a stack overflow? Wait, or recursion depth exceeded. If if x not in, I'll make it itself. Isn't that what you're supposed to do? Oh no, wait. Like, okay, what's the parent? Oh no. Okay, I'm gonna look at. I need to look at the cookbook real quick. I want to find the root of the element. Oh, okay. I see. Okay, I was doing it right, but I was doing it right, but I was doing if it's not equal if x. It's just this. But basically what they're doing is like if. Now I just need to implement this last part. Like this. It's a small variation because I didn't want to initialize the DSU with all of the points. If the parent, I had to, bro. It's already been an hour. If x is not equal to x, self dot parent x equals self dot find parent x. Done. Okay. Then what we'll do is what we're gonna do now is print point A and point B. Then we'll print the x coordinate times point. What? Too high. Let's work on the. Let's look at the test example. Oh, wait. We need to do 9. I don't think we even need to. Oh, okay. I think I know a way we could just. So we connected 216 and 805 are the last connected. What? Like obviously my DSU is wrong. Let's see, union find X. That's what I did. Let me copy and paste this part. Yeah, I pretty much had most. It was our implementation was pretty close. But I think maybe the one thing I didn't do is just initialize it properly. Maybe I need to just initialize it with all the points first. But let me try this. Like this. If if self dot parent. How come they don't increase the size of these ones? I need to review my union find. I'll do that after though. Two sixteen and 117. Bro, yeah, I need to review my union find. But essentially, what we do is did connect. Paul, I think all we need to do is like if we connect them, we just push them here. And then we do should get 216. Yeah, it's just like my union find implementation was just cooked. Other than that, woo! All right. Now let's see. Paul, you did you get that part? Okay. Now that's pretty much what we need. That's pretty much day 8. The only thing that I probably need, like as a reflection, I probably need to go study Union Find and make sure that I never forget that algo. That's kind of like my debrief right there. But I think like our intuition was good and we figured out what we needed to do. And we were able to solve it. Just like the implementation detail, we messed it up a bit. Make sure we never forget how to implement Union Find. It seems easy because it's such a small algo, but like realistically, it's pretty hard to implement. But all right, let's move on to the next day. It's already 10. It's crazy.